So I'm talking about the stellar initial mass function and how it affects the efficiency of galaxy formation. So we saw this early on from Ben Moster. So galaxy formation is quite inefficient. It peaks at around 20%, and then in massive galaxies, massive halos, it drops quite precipitously. So in the last few years, there have been many different techniques used to measure this. Abundance matching, and there's weak lensing, and the satellite kinematics, and they all tend to agree on the shape and the normalization. But one thing they all tend to assume is that the stellar masses are derived using stellar population models and an initial mass function. So why is it important? So the IMF, dn by dm, the important thing to know is that the light in an old stellar population is typically coming from these stars around 2 solar masses, because all the more massive ones have died, and the lower mass stars just don't give off much light. But then the mass is either coming from the low mass stars, especially if you have a steep IMF, or it comes from the remnants from the high mass stars. And then the other reason why, sort of more subtle way why IMF is important is for gas recycling. So when you in a stellar pop model, how much the gas, you may form one solar mass of stars, but by 13 years later you may only have half a solar mass left. Then for modeling in the models, maybe not so much for massive galaxies, but your IMF determines the amount of high mass stars, which determines your supernova rates. Okay, so what we know about the IMF, so in the Milky Way you can do star counts, and then that's what Salpeter found, this slope of minus 2.35. And then you can go deeper, and then you find that there's a turnover. And so this has been the canonical IMF Milky Way, either Krupa or Chabrier. They differ very slightly. And then you can go to galaxy dynamics. So this doesn't care about what type of mass it is, it just measures mass. And Eric Bell showed that the Salpeter IMF is too heavy for spiral galaxies. Right, there just isn't enough dynamical mass. And also was shown likewise for early type galaxies, at least the fast rotating types, the dynamical masses don't allow a Salpeter IMF. So up until a few years ago, everyone's happy with the universal IMF because all the data in the local universe supports that. And if you allow the IMF to vary, it just creates a whole can of worms. Okay, so So I'm moving on to some of the ways in which you can constrain the IMF. So the most basic thing is you can just look at upper limits from strong lensing. So this is very similar to the Maxwell disk approach that Eric Bell used. So this is a gravitational lens, this is the foreground galaxy, and this is the background thing. It's been stretched into an arc. So strong lensing measures the mass within this region very accurately. And then you can take your stellar pop model, and you can measure the mass also within the same region. And then for a physical IMF, you have to have f star less than 1. So we did this for spiral galaxies, these blue points, or galaxies with disks, I should say, and then also for ellipticals with slats. And then if you look at the stellar mass versus the lens mass for Chabrier IMF, everything is below the line, except these, which are really big error bars. So everything is consistent with a Chabrier IMF, as expected. Then if you put in a Salpeter IMF, you find that for lower mass galaxies, more than half of the points are above in this unphysical region. So this is telling you that this IMF is not physical for these galaxies. But if you go to the massive galaxies, massive elliptical galaxies, you can almost double the mass, right, relative to Salpeter IMF. So there's a lot of room in massive galaxies for more mass, whether it's dark mass or non-baryonic or baryonic dark matter. So then the next thing to ask is, well, how much dark matter do we think is actually going to be in these galaxies? So this is a picture of the galaxies from the SLAC survey. So it's a big collection of gravitational lenses from Sloan. Most of these are early type galaxies, or there are some disky things in there. And so what you can do is you can put in dark matter halos, so that the lensing gives you the mass of the Einstein radius. Sloan gives you the velocity dispersion. They also have some weak lensing information because they have HST data. And then you can build a scaling relation model. And then if you put in an NFW halo, you find the stellar mass that you need needs to have a salpeter type normalization, and there's some evidence that there has to be mass dependence. So SPS mass is your mass from the step-up model, M star is the true mass you put in your model, and this here would be if the mass was equal to a Milky Way, so either a Cooper or Chabry. And so whatever halo you put in, whether it's NFW or a contracted halo, they require more mass than you would predict from a Milky Way IMF. And then also in terms of the chi-square, this model is favoured more than these models.
Doesn't this just contradict the previous analysis?
No?
Okay.
This has not.
No, I know, but the argument was that salpeter overproduced.
That's only for the low mass galaxies.
Yeah.
For the high
So
mass
this is just for the very high
galaxies,
mass ones.
Yeah. Well, it's mostly for these galaxies, the ones that are the SLAX galaxies, whereas the coloured ones, like below 230 kilometers a second,
okay,
they're statistically.
So you're saying that this only would apply to a big galaxy, the Auger analysis?
Yeah.
Okay.
Okay, so then in the same year, so the thing is that we have this this result from lensing that says, well, there's more mass than you'd expect from Milky Way IMF, but that can't say whether the mass comes from low mass stars or stellar remnants. So there's this paper by Peter Van Dokkum and Charlie Conrad that came out, and so low mass stars, if you're really low, you get this feature, the sodium 1 feature and the swing forward band feature, and when you're a little bit more massive, this feature doesn't appear. So if you can measure this feature, then there's a way of counting the low mass stars in the galaxy. And so they did this, and they're comparing, these are the predictions for different models from a bottom light, the Kruper, salpeter is in green, and then they found evidence that you need to have quite a bottom heavy IMF. Yeah, shake your head, Eric. Okay, so if you believe this result, then it's saying that the higher masses that lensing studies find are because there's more low mass stars. Then they did a little more work on more galaxies, and they're fitting a larger region of the spectrum, not just the sodium 1 and wing forward feature. And they find big samples and some correlation. So this is the stellar mass they get from fitting all the various lines, and this is the mass they get from a Cooper IMF. So this is the Milky Way IMF. I think these were the galaxies they started off in their first paper. So they picked the most massive nearby thing, and they have a very, very heavy mass function. But then there's a trend that goes down. This is the bulge of M31, and so there's a trend with dispersion that goes down to the Milky Way. And I think the Milky Way would be somewhere around here in terms of the velocity dispersion.
When you say Milky Way, what do you mean?
I just mean the velocity dispersion of the Milky Way. So about.
You mean the bulge?
Not the bulge. I mean the mass scale. So it would be a sigma of about 120 kilometers a second or something.
And it's a local solar neighborhood IMF. What IMF are you using?
They're using a Cooper.
Normalized what? Because there's a mass in here that matters by a factor of almost 2. What's the break mass?
I don't know. I don't know if it's 2001 or 2002 IMF.
I think they're using the half solar mass.
Yeah.
I think that's what they're using. At least
But you can kind of guess from the difference.
It's half solar mass to get their plot.
Yeah, you might be able to work it out from the difference between salpeter and this thing. So actually interesting that the most strongest correlation they found wasn't with the dispersion, but it was with alpha abundance. So this is telling you about the time scale of the star formation. So I guess the first thing you might ask in terms of consistency is to go back to dynamics. So these are all Sauron galaxies, and these have total dynamical masses. And so this is the spectral stellar mass to light ratio versus the dynamical mass to light ratio. And everything has to be in this region. So there are some galaxies up here, but you can just explain that just from measurement errors. Right? So some galaxies are here and they get scattered over. So the masses are consistent with dynamics. And then another consistency to check on the method is to go to dense galaxies. And I'll explain in a few slides why we expect high-density galaxies to have low dark matter fractions. And so we select galaxies that have surface densities using a Chabry IMF greater than 2,500 stellar masses or parsec squared. So in the size mass plot, this is just a straight line cut, and we're picking all these galaxies here. And this just showed examples of what they look like. So this is the normal early type, and these are the more compact ones. And then we just do a spherical genes model fitting the aperture velocity dispersion. And since the aperture is bigger than the effective radius, because it's quite compact, then the anisotropy doesn't really matter. And then, so this is the dynamical mass versus the stellar mass from the Chadwick IMF. And then the offset is consistent with normalized salpeter IMF. And then you can fit a slope, but depending on how you're fitting it, right, if you do dynamical mass and fixed stellar mass, there's actually no slope, the slope is 1. There's no trend. And if you do the other way around, you get a 1.23. So the true slope depends upon where your errors are coming from, how much is dynamical mass and stellar mass. So I don't want to get into that, but the point is the normalization is basically salpeter. So these galaxies have an IMF that's quite heavy. So why do we think mass follows light in these galaxies? And this goes back to work that Courtois and Ricks did. So this is the contribution of the disk to the total at 2.2 scale lengths. And this is, if you change the size of a galaxy, the scale length, then you change the rotation velocity at 2.2 scale lengths. And you change it in this way. So there's different sorts of galaxies with different dark matter halos. And then the point is, if you find galaxies that have this correlation of -0.4 or below, then you expect to have very little dark matter. So you can do the same thing for an early type galaxy. So again, this is d log v, the circular velocity at the effector radius is a function of varying the effector radius in terms of the Dutton fraction. And so for an FW halo, you have these black lines, and you can vary the stellar halo mass by an order of magnitude, and you get this little shift, and you can vary the concentration by a factor of 25, and it really doesn't make much difference. And you can show analytically, just really no integrals hardly, that this ratio depends upon the slope of the dark matter fraction at that radius, right? And so we expect dark matter halos to be somewhere between 0.5 and 1.5. But even if you had a dark matter halo that had a slope of 2, a density slope of 2 at the half radius, if you can measure a slope of -4, then you expect the dark matter fraction to be less than 20%. So where are the galaxies, the dense galaxies, in what do they have for this parameter? So if we go to Sloan, we can measure the velocity mass relation and the size mass relation. And then we can take a mass bin, and then we're going to measure a size offset and a velocity offset. And we're going to plot the two against each other. If you do this for all the galaxies, then you get this relation, and you can fit a line to this, and the slope is -0.3. And so for the Vero fundamental plane, you have a slope of -0.5. That's basically the mass follows light. That's this thing here. If d log v by d log r is -0.5, then you have no dark matter. That's essentially a mass follows light model. But then if you look at here, I noticed when I made this plot, these galaxies had a slope that was -0.5. And these are the galaxies that offset from the size mass relation. And so I have not been able to make a model that matches this without mass follows light. So I think this is quite good evidence that if there is dark matter in these galaxies, it's very small. And then what's interesting is then you go to, we bin the galaxies by velocity dispersion, and then Charlie used his models. So I measured the dynamical mass using mass follows light, and then Charlie used his models to measure the mass using the spectra, using the stacked spectra, and we get pretty good agreement. And there's even room for some dark matter in these galaxies. So this is a consistency check that the models, the spectral models that are saying that these IMFs, the higher mass ratios are coming from the low mass stars. And then there was also, around the same time, there's work from the Atlas 3D survey. So this is showing the ratio between the stellar mass derived from a dynamical model versus salpeter versus velocity dispersion. And I mean, there's a really big scale here. And you might think, it's like a constant almost, but there is a trend with velocity dispersion. And this slope, 0.26, is very similar to the slope that we find from the dense galaxies. It's slightly shallower, but I'll show a plot at the end that shows everything is completely consistent. Okay, so one thing you may say about all these studies is, well, the Charlie's stuff was the centers of a few nearby galaxies. At 3D, these are nearby galaxies are basically the disk galaxies, or their lenticulars, and their satellites. And the dense galaxies where they're a subset. So what about the full population of early type galaxies? And so I'm going to show now some mass models we do of trying to model the full population. So we have stars and dark matter. The stars have 4 parameters. And the main uncertainty here is the stellar mass normalization. And for the dark matter halo, we have NFW halos, and then they're modified by some unknown halo response, either contraction or expansion. And so the structure we're basing our work from Luc Samard, so we're using the exponential plus de Vogler fits. And then halo masses, we're using results that I compiled from weak lensing and satellite kinematics, and the concentration mass relation from lambda CDM. So some assumptions, well, we're using spherical Jeans equation to predict the aperture velocity dispersions. We're assuming that there's no stellar M over L gradient, so that the light profile is actually describing the true stellar mass profile up to a normalization. We have constant anisotropy, although this really doesn't make much difference. But more important, I suppose, and if you wanted to disagree with any of the assumptions, it might be here, because I'm assuming that the scattering in the galaxy size is uncorrelated with the form of the halo response, scattering the halo mass, and scattering halo concentration. So this is sort of an important assumption I'm making. So then, the first thing we do is then we use the velocity dispersion mass relation to constrain these 2 parameters. So we have 2 parameters in one relation, so we're going to have a degeneracy. That's okay. So this is the same plot, velocity dispersion versus stellar mass, using a Shabrik IMF, and we tune the model, the offset between the true stellar mass and the Shabrik IMF mass, just as a power law. And the interesting thing is all these models have the same slope, 0.14. So the true stellar mass divided by the SPS mass scale is like 0.14, and they just have different normalizations. So there's a mass formalized light model, there's one with halo expansion, with NW halos, some weak contraction, and this is adiabatic contraction. And even tried to concoct a model that had a universal IMF, but had expansion in low mass galaxies and contraction in high mass galaxies, just see what happened. And then, so the second step is use this fundamental plane correlation. So again, this is the change in the size divided by the change in the dispersion when you change the size at fixed mass. This is the viral plane, and what we see is that lower mass galaxies have a much stronger correlation. So just to recap where this comes from, we take the velocity mass relation, the size mass relation, we take a bin and we look at the correlation in sigma as a function of correlation in size. Okay. So when the size goes down, the sigma goes up. But how much it goes up by, that's the thing we're fitting to. So these are our models. So the color is the model, and the dash region is like a 1 sigma uncertainty. So the thing that really shocked me when I did this was the mass formless light works at so much of the masses. I thought this is crazy because we know there's dark matter halos, but it doesn't work at the very massive things, which is kind of good because the lensing results were from the very massive systems, and they've shown that mass formless light does not work. And the FW models work reasonably well at very massive systems, but when you have adiabatic contraction, then you predict too much, the correlation is just too weak. And this is simply because when you've got more dark matter, you change the size of a galaxy, but the circular velocity, the velocity dispersion just doesn't change because the dark matter is such a large dark matter content. Okay, so I'm basically almost done. So I wanted to summarize these results. So all these different models, they have the same scaling between the stellar mass, the true stellar mass, and the stellar hot mass versus the stellar hot mass. And so all of these fit the fundamental plane. No, so all of these fit the velocity dispersion mass relation, the size mass relation, halo mass, stellar mass. They just differ by the fundamental plane. And the fundamental plane is basically picking out a model that's close to mass formless light. And then high masses, you kind of want some dark matter halo. And this green cross was the result that Matt Auger found from combining strong lensing and dynamics. This dot here, the magenta one, is what we got for the dense galaxies, which are a subset of these things. And maybe we did the dense things first because we thought, well, mass formless should follow light, but it turns out that the whole population around this mass, I would argue mass follows light. And this other, across this point here is a result we had from, we looked at massive bulges, because these have declining rotation curves, and the only way you can fit the centers is with a heavy bulge. Then I then took this stellar mass, and because I have a scaling relation, the fundamental plane, then I can, actually in the Faber-Jackson relation, then I can predict the velocity dispersions, can compare with some other results. So these lines are the same for my models, and then, so these are some other models here. We have the grey line is the result from Atlas 3D. The points I've binned from Charlie Conroy's work, and the squares are from Tommaso Treu. So the trend is basically the same from all these models. There is some offsets, normalization offsets, which maybe that's interesting. Maybe it's just that everybody is using a different way to calculate the SPS mass, and so that could possibly make some of these differences. But I think the interesting thing is that the trend is the same, and in the very massive galaxies, everyone is basically consistent. That there's the stellar masses, the true stellar masses are a factor of 2 higher than what you predict from a Milky Way. Okay, so the summary.
Mild contraction model works.
Huh?
Mild contraction model.
Yeah, in the massive galaxy it works.
Mild contraction.
Yeah. Well, it's just it's halfway between no contraction and adiabatic. Okay, so what's relevant for this conference is the star formation efficiency. So stellar mass divided by halo mass is a function of the cosmic baryon fraction. And this is what you get. This is I think this was from Ben Moster's 2013 paper. And then if you take a true stellar mass, what I argue is the true stellar mass, then it's basically going to increase, in most halos that host an Euler type, mass Euler type, it will increase the stellar mass by a factor of 2. So this adds to the result we just heard earlier from Mariangelo. The light in most of these that were used to go to this was underestimated by a factor of 2. And so you've got a factor of 4 higher mass in these massive systems than we thought previously. And that is going to have an effect on what mechanism is responsible for quenching these galaxies. Okay.
I'm going to go from the back to the front. Stop.
So this is a really clever way of getting at something we've done completely differently, because we've actually gone after the stellar lines and they compared them directly to the lensing masses. What we find at the moment is that it's hard. Can you put up your previous point, actually? It's hard for us to get significantly above saltpeter with the current constraints from the stellar population models. We get to slopes that are about minus, if saltpeter is 2.35, we can get up to about 2.7 or so. But it's really hard to get much above that, even at 350 kilometers a second. So I do think that would indicate that your slight contraction models are slightly better probably than your mass follows light models, at least at the massive end. At the low mass.
Yeah, so actually so the mass follows light, I wouldn't advocate that at all for the 300 sigma galaxies.
At the low mass end, we're actually getting things that are much closer to Pluto saltpeter at sort of velocity dispersions of 100 to 200 to 150 kilometers per second. So it's not clear how much that is going to affect these results, but maybe it does argue that, as we just heard, for maybe more like mild contraction than for something more extreme like mass follows light, even at the lower mass galaxies.
I guess one of the things that does affect things a little bit is the anisotropy.
Yes.
So I'm assuming isotropic, and if you add a little bit of anisotropy, that'll shift all my models down a little.
Nick?
This is not the relevant to the topic of conference, but in the war spheroids now there is a very serious evidence that mass function is actually top light. And so it follows the same trend all the way to stellar masses, like 10 to the 5 stellar masses.
Okay.
And they are just from stellar counts. Right? So that's actually something very hard to get rid of, because they're actually counting individual stars. So that this trend continues all the way to very, very low masses.
Okay, good. That's interesting.
Okay.
So I wanted to ask a quick question about what's your take on Russell Smith's argument that if you have a universal IMF and then calculate residuals from that, from both dynamics and stellar lines, that the residuals don't correlate with each other like you'd expect if it was an actual IMF offset, but that they correlate. The stellar lines correlate with the stellar lines, and the dynamics correlates with the dynamics, smelling like systematic errors. So Russell Smith made that argument. I wanted to know your take on that. The second question is, for the stellar population modeling, how much does anyone use relatively complicated extended star formation histories for the early types like we'd expect in a hierarchical universe? Because I suspect that makes a difference to the it does make a difference to what the present day mass function looks like around where the around kind of
Yeah, okay, so in
mass
terms of the in terms of the IMF,
yeah.
you can kind of ignore all that stuff, and the results that I showed for the fundamental plane in dense galaxies, they're just saying what is the true stellar mass compared to what the mass that MPA-JHU tells us.
I'm
So
saying
I would argue that from the dynamical modeling, that mass needs to be higher. In terms of what does it mean in terms of IMF, that's a separate question.
I understand that. I'm just saying that there's no guarantee that MPA-JHU is necessarily correct.
Correct, yeah. I mean, that is a possible solution out of this. But then you have to then explain why. Where'd it go? The stuff with the, we did, so Charlie Conrad did his models on the same galaxies that we had the dynamics on.
Mhm.
So, oh, this keeps messing up. It's supposed to make it simpler, but.
So I guess what I'm asking is, what do you know what kind of star formation histories Charlie used?
No, I don't actually.
I-
I just do the manual way.
Scott is positively bursting to address
Oh.
the second part of your question.
I have an answer to both of that question and your second question. That Charlie uses purely SSP models.
I
for these
know.
galaxies. But I have a former student, Chiara Spiniello, who's done a lot of this work, who's looked at multi-population models. We haven't published it yet because we're still trying to understand what it means. But the simple answer, the first pass answer to your second question is that unless the IMFs are radically different in the different populations, it makes no difference to the IMF determination. If you take two models that had wildly different ages, wildly different metallicities, you add them together, they produce the same IMF that they started with, unless they have wildly different IMFs, in which case they produce something in the middle. Basically, IMFs add like roughly mass-weighted vectors of the IMF in the composite stellar population model. So if the IMF is changing with time, like Peter Van Dutton used to advocate, then yes, you will get a different IMF than what you think you have. But in a simple stellar population model or a simple evolutionary model where the IMF doesn't change with time, the IMF is what you get out of the models. Whether you believe that the IMF is the thing that's varying is a completely different question. If you have an hour, I'd love to sit down with you and show you a lot of Otherwise,
I'll make that ours.
Aaron, did you want
Yeah,
to
so I just wanted-
this time?
The relative Russell Smith question.
Yeah.
So I don't know if this answers it, but these are the same galaxies. They have dynamics and the stellar masses.
So is
So the
Russell
averages
Smith's.
agree.
So is Russell Smith's.
Okay, but I wouldn't worry about, I wouldn't worry about the scatter around these things, right? There's going to be errors in both of these. So,
scatter diagrams are notoriously difficult to interpret.
so when I show the scatter diagrams, I'm modeling all the errors.
Can we have the next speaker set up while we take it on your question?
So if the IMF is going to vary, then you would expect very local conditions, so you wouldn't expect the mass to light ratio to be independent of radius, as you assume.
Yes.
And I think there was also a paper showing that there is some dependence. So,
Yeah, I did that.
so you assumed here and you did it at the same time, so how does the fact, you don't assume it? What changes?
I'm not sure what would change. I guess if there was a model that predicted how the IMF would vary with radius, then we could put it in. But so in the paper that I wrote, we had spiral galaxies with large bulbs.